Hello everyone. Before you start watching this lesson, I am assuming that you already have a basic understanding of the various trigonometric formulas like sine of x plus y, cos of x plus y, tan of x plus y, the general solution of sine, cos, tan, how the sign of the trigonometric functions changes with the quadrant, like sine is positive in the first and second, negative in the other two. Cos is positive in the first, negative in the second, negative in the third, and positive in the fourth quadrant. Tan positive in the first, negative in the second, positive in the third, and negative in the fourth quadrant. So you should know all this before you start watching this lesson. I will cover all these topics in a later lesson. So let's begin with properties of inverse trigonometric functions. I will discuss the properties in batches of similar formulas. To prove the first one, assume sine inverse 1 by x is equal to y. So 1 by x equals to sine y. This can be written as x equals to cosec y. Now this implies that y is equal to cosec inverse x. But y was sine inverse 1 by x. So sine inverse 1 by x equals cosec inverse x. Similarly, you can prove the second and the third formulas. An important thing to note is that the trigonometric functions are defined on their principal value branch. So sine inverse 1 by x is defined only from minus 1 to 1. So x has to be less than or equal to minus 1 or greater than or equal to 1. Similarly, cos inverse is also defined from minus 1 to 1. So here x has to be less than or equal to minus 1 or x has to be greater than or equal to 1. And for tan inverse 1 by x, tan inverse is defined on the whole set of real numbers, but this formula holds only for x greater than 0. If x is negative, tan inverse of a negative value returns an angle from minus pi by 2 to 0, and cot inverse of a negative value gives an angle from pi by 2 to pi. So these two will never be equal if x is less than 0. Please note that we are only talking about the principal value branches. Since 1 by sine x is equal to cosec x, you might be tempted to learn these formulas in a similar manner by saying that 1 upon sine inverse x is equal to cosec inverse x. Please note that this is not true. So here is the next batch of inverse trigonometric formulas. To prove the first one, assume that sine inverse minus x equals to y. So minus x equals to sine y, x equals to minus sine y. Then this can be written as sine of minus y. Since sine is an odd function, minus sine y can be written as sine of minus y. So therefore, sine inverse x is equal to minus y, and y is sine inverse minus x. So sine inverse minus x equals to minus sine inverse x. You can prove the second and the third formulas using the same method. Since tan and cosec are both odd functions, this transformation will hold for both of them. Recall that for cos, sec, they are not odd functions. Therefore, the formulas are not the same for cos and sec. Cot inverse x is also an odd function, but we can't use the same formula for cot because cot inverse is defined from 0 to pi. Here are the formulas for cos, sec and cot. Cos inverse minus x is equal to pi minus cos inverse x. This can be proved by assuming that cos inverse minus x is equal to y. So x is equal to minus cos y. Now minus cos y can be written as cos of pi minus y. Recall that cos of pi minus x is equal to minus cos x. So cos inverse x is equal to pi minus y, and y was cos inverse minus x. So cos inverse minus x is equal to pi minus cos inverse x. You can use the same method for sec. Here minus sec y can be written as sec of pi minus y. But for cot, it is also an odd function. So when you get to this step, x equals to minus cot y, you have two options. You can write it as x equals to cot minus y or x equals to cot pi minus y. But since cot inverse is defined from the set of real numbers to 0 to pi, we must use the first option. I'll show this with an example. Let's say x is 1. So cot inverse minus 1. It can be taken as minus pi by 4 or pi minus pi by 4, which is 3 pi by 4. Since we have defined the range of cot inverse from 0 to pi, we must take the second answer. These are the next set of formulas. To prove the first one, assume that sine inverse x is equal to y. Then x is equal to sine y. Now sine y can be written as cos of pi by 2 minus y. So therefore, cos inverse x is equal to pi by 2 minus y, where y was sine inverse x. Therefore, sine inverse x plus cos inverse x equals to pi by 2. You can prove the other two formulas using the same method. Since tan of pi by 2 minus x is equal to cot x and sec of pi by 2 minus x is cosec x. These are the next set of formulas. To prove the first one, assume that tan inverse x is equal to alpha and tan inverse y is equal to beta. So if I write the formula for tan of alpha plus beta, which is tan alpha plus tan beta upon 1 minus tan alpha tan beta. Here we can write x as tan alpha and y as tan beta. So I can write this statement as tan alpha plus beta is equal to x plus y upon 1 minus xy. If I take the inverse on both sides and write alpha as tan inverse x, tan inverse y is equal to tan inverse x plus y upon 1 minus xy. To prove any inverse trigonometric formula, you can think of any inverse function as an angle. And to prove that the LHS is equal to RHS, keep in mind the trigonometric formulas that you have learned before, like tan alpha plus beta is equal to tan alpha plus beta upon 1 minus tan alpha tan beta. Using this method, you can prove any inverse trigonometric formula. Similarly, for the second formula, if you remember the formula for tan of alpha minus beta, you can prove the second statement as well. Now you'll notice that the third formula, the LHS is same as the first formula, but the RHS is not the same as the first formula. How is this happening? This is because the first formula is only valid when x into y is less than 1, and there's a condition for the second formula as well, which is xy is greater than minus 1. So what happens when xy is greater than 1? The formula turns into the third formula. This is happening because the range of tan inverse is from minus pi by 2 to pi by 2. Since we are adding two tan inverse functions, this LHS can have a range from minus pi to pi, but the tan inverse will only give a value between minus pi by 2 to pi by 2. If x and y are both greater than 1, then this will have a value greater than pi by 4 and this will also have a value greater than pi by 4. So the addition of these two values will give a value greater than pi by 2. Hence we add this pi term to get the solution. The inverse trigonometric functions always have some conditions given beside the formula. This is because the range of the inverse function is limited. You must be very careful while you're solving problems. You might forget these conditions while you're solving the problems, but that's not a big deal. If you know the domains and ranges of the inverse trigonometric function, just calculate the answer using the easiest trigonometric formula. You don't have to remember this one. If x and y are both greater than 1, calculate tan inverse x plus y upon 1 minus xy. But you know that x and y were greater than 1, and so the solution should have a value greater than pi by 2, but you will get an answer between minus pi by 2 to pi by 2. So you can just add a pi term to your answer to get the solution. This is possible because for the general solution of tan x equals to tan y, x can be n pi plus y. So you can add any number of pi terms or subtract any number of pi terms from any side of the equation to make the LHS equal to RHS. So this is the next set of formulas. To prove the first one, look at the LHS and the RHS. It has a tan inverse term and a sine inverse term. So you must use a trigonometric formula that involves sine and tan. Assuming tan inverse x as an angle, take tan inverse x is equal to y. So x equals to tan y. Now if I take the sine of 2y, I can write it as 2 tan y 1 plus tan square y. Take the inverse on both sides, it becomes 2y is equal to sine inverse 2 tan y upon 1 plus tan square y, where y was tan inverse x. So 2 tan inverse x is equal to sine inverse, and tan y was x, so 2x upon 1 plus x square. Similarly, to prove the second formula, you will use cos 2y is equal to 1 minus tan square y upon 1 plus tan square y. And to prove the third formula, you will use tan of 2y is equal to 2 tan y upon 1 minus tan square y. There are many more inverse trigonometric formulas which involve sine, cos. So to prove any inverse trigonometric formula, the general method is to take the inverse function as an angle and see the terms on both sides of the equation. Here it was tan and sine. So think of a formula you know which use sine and tan at the same time, which was sine 2y is equal to 2 tan y upon 1 plus tan square y. So using this method, you can prove any inverse trigonometric formula. You should also make sure that the domains and ranges of the inverse function is also satisfied, because of which there are conditions imposed on the formulas. Like the first formula is valid only when mod x is less than equal to 1. The second formula when x is greater than equal to 0. Third formula only when x is between -1 and 1. These conditions are not that important if you remember the domains and ranges accurately and you remember the general solutions of the trigonometric functions. So this is it for this topic. Thanks for watching.